Hello everyone, my name is Zhang. I'm going to discuss our paper, Budgeted Adversarial Network Resource Utilization Games. Here is a list of topics we will cover. We study network games with a network designer and an adversary. There are many real-life applications like message sending and intercepting, tackling down human traffic networks, and maybe right now of the most interest to the world, restricting the infectious travelers in the pandemic. In the pandemic setting, travelers carrying virus without knowing it as the designer may make travel plans in response to different levels of restrictions on different types of transportation and routes, which are placed by the government playing the role as the adversary. All the previous examples can be modeled as a zero-sum game on a flow network, where the designer chooses path to route flow and the adversary intercepts it by choosing edges to attack. The adversary has a budget constraint and pays for edges attacked. The adversary utility will be the amount of flow intercepted. The notion of attacking cost and budget constraint is very important in our game. Previous works include incorporating the attacking cost into the objective function directly in a spanning tree setting, adding a budget constraint in a network setting but only attacking one target, and attacking multiple targets with indifferent costs. We extend the problem to a general flow network with different costs to attack and later on different costs to design the flow network. Despite that, generally there are exponentially many possible paths in the network. We present fast polynomial algorithms using combinatorial approaches. Let's look at the network routing adversarial game with a very simple example. First, we have a flow network with the designer required to route a total amount of 1. The flow is from A to B. Every possible path is usable, as a traveler may choose any possible route that fits the need. Now we add the adversary's attack, marked in red. An attack on an edge means the level of interception. The final effect of attack on any path is the summation of attacks on all the edges on that path. For example, on path 3, the attack is 0.3 plus 0.1. The attack on a path means the fraction of the flow that is intercepted. If we apply the pandemic traveling setting, this would mean the amount of infectious population traveling on this path that is tested and stopped from going to the destination. The adversary's utility is the total amount intercepted. Our goal is zero-sum, so that is also the amount the designer loses. Next, we look at the cost of attacking, marked in blue. Each edge is associated with an attack cost. The cost to the adversary is the product of the attack level in red and the cost in blue. There is a budget to the adversary. The overall cost should not exceed the budget. Here is a Nash equilibrium on this network. The adversary spends the full budget 3 to attack edge 1, 2, 3 by the same level 0.5. Edge 4 is not attacked. Every path is attacked by 0.5. The adversary utility is 0.5 and the designer utility is minus 0.5. In general, the number of all possible paths is exponential, so we turn to a combinatorial approach. We look at the adversary's intuition. If the adversary chooses to attack a path, the attack should be placed on the cheapest edge. Among all paths that carries flow, the adversary should only attack those with the highest benefit. The designer's goal in turn is to minimize the highest benefit in the network. In a Nash equilibrium, the attack has to cover every possible path. So the adversary must attack a cut. With limited budget, the min cut is the obvious choice. In this case, it is marked by the red dashed line. The designer's job is to make sure that every edge in the min cut represents the same benefit to the adversary. We use the costs as capacities to produce a max flow. The amount of the flow will be C star, which is the cost of the min cut. We then scale it back to 1, and we get a flow of amount 1 with no edges benefit higher than the edge benefits in the min cut. Given this flow, the adversary will attack every min cut edge with the same level. The level is also going to be the final utility of the adversary. It does not matter if there are multiple min cuts, for the highest attack benefit is still the same on any min cut edges. The adversary may choose any min cut to cover. The overall time complexity is big O of VE, mainly to generate a max flow. There may be multiple Nash equilibria, but they all have the same final utility. We next discuss the two-commodity version. The focus is still on min cuts. The graph here is an abstract representation of different min cuts. Designer 1 routes from A to B, designer 2 from A to C. Each is required to route 1 unit of flow. So there is 1 unit of flow through C1 and C2 respectively, and 2 units of flow through C12, which is the common cut. The adversary may choose the most beneficial cut to attack first, regardless of which designer the cut belongs to. Without loss of generality, assume cost of cut 1 is lower than cut 2. There are 3 cases. The first case, if the common cut C12 presents a higher benefit than C1, then the adversary will simply focus on that. In this case, both designers will route a two-commodity flow respecting the edge costs, then scale it like what we did before. Both designers in this case suffer the same loss. Case 2, if C1 is more beneficial, then the adversary attacks this first. By the properties of two-commodity flow, designer 2 can always route a flow that is less beneficial than designer 1. In case the adversary budget is not enough to cover C1, it is going to be a partial attack on C1. The adversary gains from intercepting designer 1. Case 3. If the adversary has more than enough budget to fully cover C1, the additional budget will be spent on C12, the common cut. The attack is going to be a linear combination of attack on C1 and C12, making sure that designer 1 is still fully intercepted and designer 2 is partially intercepted. In this case, since designer 1 loses all the flow, no matter what, the joint flow is designed so that every edge related to designer 2 has that same benefit property. Overall, the time complexity is V cubed in all three cases to route a two-commodity flow. In the next version, we want to add restrictions to the designer too. We focus on a bipartition or a cut. There is only one designer in this case. Both the designer and the adversary has a budget, and each edge is associated with costs to both design and attack. We first sort the edges by designer costs. In this case, the designer is no longer free to design any flow to make sure all edges in the cut is equally beneficial. With limited budget, the designer can only choose the cheapest edges to route. We first write the linear programs for the two players. LP1, 2 are the primal and dual for the designer. LP3, 4 are for the adversary. If we solve LP1 and LP3 at the same time, these are no longer linear programs, since the objective function is the product of designer and adversary strategies. Therefore, we combine the two dual programs and add in the missing primal constraints. Now we have a primal and dual program whose complementary slackness conditions satisfy the designer and adversary at the same time, which means the optimal solution to LP5, 6 will be the optimal solution to LP1, 2, 3, 4 at the same time. Note that the variable gamma here is the cost efficiency for the adversary or the attack benefit, which is quite intuitive. On the other hand, omega is somewhat similar to that for the designer, but it is quite hard to make economic sense directly. But with it, we can set up a system of equations to solve the attacks. The Nash equilibrium is produced by satisfying the conditions. The designer first attempts to include as many edges as possible to make the flow on them equally beneficial to attack. There will be k hat minus 1 such edges, and there will be one last edge which is less beneficial because of lack of designer budget. The complementary slackness conditions guide the optimal attack. If the adversary attacks the first t edges, we can calculate the attack levels on each edge. Attacking the first t edges also requires an adversary budget BA of t. Now with the actual adversary budget BA, we can search for the number of edges t such that the actual budget falls between the range from BA of t minus 1 to BA of t. With that, we can produce the optimal attack as a linear combination of that two sets of attacks. There are two boundary cases where BA is either too small or too big, but they can both be handled easily. When the optimal attack is determined, the optimal design can also be calculated given the number of edges involved. Since now the number of edges involved is more than being optimal, the designer will be forced into using more edges than necessary and overrouting on the first edge. This version of game can be solved much faster than solving the combined linear programs 5 and 6. For the most time is spent on sorting the designer costs. If the edges are given in sorted order, all the remaining calculation is solving a couple of system of equations. To conclude, we studied adversarial network games on general flow networks with the adversary constrained by budget in 1 and 2 commodity flows, and provided combinatorial solutions to overcome the exponential number of paths. We also studied the game on bipartite networks with budget constraints on both the designer and the adversary, and provided faster solution than solving the linear programs. Future work may include extending the version with budgets on both parties to a general flow network. Thank you.